Okay, so this was what we've done so far. We know how fast a quantity is changing at every moment, rate of change. We want to know how much of it we have at every moment. So we were developing accumulation from a given rate of change. So now, as you've learned in chapter 6, we're going to reverse it. So now it's going to be, we're going to start with accumulation function, and we're going to develop the rate of change function from the accumulation function. So what's this? This is, you know how much of something you have at every moment, and you want to know how fast it's changing at every moment. That's our new endeavor here. Okay, what we did. Exact rate of change, to approximate rate of change, to approximate accumulation, to exact accumulation. And then doing all that hard work, we earned the right to streamline, go right from exact rate of change to exact accumulation. And we do that just by writing down the integral, knowing where it all came from, right? Knowing where it all came from, we paid our dues, we earned our right to write down an exact accumulation function straight from exact rate of change without doing the stuff in the middle. Okay, so now we're going to reverse it. What are we going to do? We're going to start with an exact accumulation function. We're going to build an approximate accumulation function from that, from which we'll get our approximate rate of change, and then we'll achieve our goal of getting exact rate of change. And then we'll earn the right to get an exact rate of change function directly from the exact accumulation function. So that's what we're doing now, what we will do. Okay, so where do we find exact accumulation functions? Where do we find exact accumulation functions? All right, well, what's another way to say what an accumulation function is? No, like what it means. Yeah, so what do we mean when we say an accumulation function? I thought you raised your hand. Oh, you know the word. Okay. Yeah. A sum, okay. But so if we wanted to, how could we say it without, it is, yeah, accumulation is literally like sum. But really, accumulation functions are just like quantity functions, just a function whose dependent variable gives us the amount, just gives us the amount, okay? So we deal with these all the time. These are the functions you're used to, having dealt with your whole mathematical career. So here's, like, for instance, the area of a square is x squared. So we can think of that. So before you thought, oh, you plug in the side length, it gives you the area. Well, now we can think about that as the area having accumulated as x increased. So a quantity function and accumulation function are really the same. So this is how you used to think of it, but now as an accumulation function, we can think of the total area is the accumulation of area at some certain rate, some rate function. So we can write it as an integral. Okay, another volume of sphere. So we can think about the volume accumulating as the radius grows. We know that given any radius, this is the volume of a sphere. But now we can think of that also as the accumulation at a certain rate. So it accumulated at a certain rate in order to give us some total amount. So any function that gives an exact amount of one quantity as a function of another is an exact accumulation function, and therefore can be represented as an integral of its exact rate function. It's just that we don't know what the rate function is. We don't know what the rate function is. We know how much we have at any moment, and we're trying to find how fast it's changing. The volume, in this case, volume is changing at any moment. All right, but this is our goal now. So we're going to devise a method to figure it out. Lots of the tools that we learned or used in the forward process are going to be helpful in the reverse process. In fact, the reverse process was going to go a lot faster because we have many of these tools in place already. Okay, questions on the general overview? Okay, so here's the area of a square. Here's this area function. We know that any area of a square is found by side length squared. So here's our exact accumulation function, the accumulation of area of a square with respect to side length. Okay, so what kind of function is an approximate accumulation function? What's its graph like? And how might we construct an approximate accumulation function from the exact function? So you read about this, and we had top hat question about this. So what kind of function and what's its graph like is an approximate accumulation function? Is it horizontal steps? No. Okay, someone says piecewise. Piecewise linear. It's a piecewise linear. And how do we construct it from the exact accumulation function? What did we say? Yeah. Oh. Yeah.
Say that 0.5, 1, 1.5 to the area function, and then just connect.
Okay, right. So it's going to be piecewise linear, and it's going to be line segments whose endpoints are points on the curve from whatever partition we choose, however we choose to set up delta x. Okay, so let's take a look at that. So here is, if we had delta x was 1, then we'd get this approximate accumulation function, the blue one, the segments. Okay, so notice each segment then is going to have a constant rate of change for its interval. So you get a constant rate of change for every interval. Okay, what if we wanted to make the approximate accumulation function better? Is this a good approximate of our exact accumulation function? Right, so it's especially in that first interval, it's too high most of the time. The accumulation is too high. And so how can we make a better approximate accumulation function? Easy question.
Go by smaller numbers.
Smaller intervals, right? Smaller intervals. So with smaller intervals, here's intervals of 0.5. You see that you can just barely see daylight now between the exact accumulation function and the approximate. You can still see that they're different, but boy, is this doing a much better job of approximating the exact accumulation function. Again, constant rates of change over each interval. Okay, so I don't have my pen. I can't write. So where can I write? Can I put the screen up and write on the board? Let's do that. It just won't show up on the video. So I'll just write down here. Okay. So if we wanted to build this function piecewise, this function, it would be a matter of what? Writing a piece for each segment. Okay, this is a review now. So did you learn how to write equations of lines given? So we have this area function is x squared. So we might need, say, that point there. We want to use exact values here. Okay? So how are we going to do this? So what will the general say? What will the general structure of this first, in this first interval? What will the general structure of our approximate accumulation function be in that first interval? Anyone think they know? Yes, sir? What's that? Times 1/2? The the length of that interval, so we got delta x at 0.5. So we need the linear, the equation for all those points. So given a value x, say right here, any arbitrary value x, current value in this first interval, what will give me the corresponding value of approximate area? Yes, sir? Okay, how did we write piecewise linear functions? One step at a time. What was the general structure of that? Anybody remember? Slope. Well, that has to do with it. Slope has to do with it. So what do we need? We want the output, right? Where does it come from? Linear function. What linear function did we use? Yeah. No, we didn't do mx plus b. We didn't do mx plus b. What did we do? What's that? Okay, it had to do with mdx. But there's more to it than that. Yeah. Right, so the new y is the original y plus dy. And then dy was, how do we calculate dy? mdx. Okay, so in this first, so we'll write it right here. What's our initial value of, in this case, area in this first interval? Initial value of area in the first interval. So you're saying 0? No, just the initial value. 0, right? So it's going to be 0 plus the change that we get for the current value of x. So any x in here, so it will be, we need the rate of change. Can we calculate the rate of change? How are we going to get the rate of change for this first segment? What is it? No, the rate of change isn't a of 0. Well, the rate of change is going to be the change in area for the change in side length. And we're going to use what we know. What do we know? We know here we have 0.5 and a of 0, area of 0.5, right? The red one, which is be 0.5 squared. So we know that point for sure. So our initial slope there is going to be change in y over change in x. So we'll call that M1. And that equals 1/2, or 0.5. So M1 is 0.5, because I know that I start at 0, 0, and I'm going to be here at the end of the interval. I'm going to be at 0.5 and 0.5 squared, because it's this area of a square. So from those 2 points, I can get the rate of change, the constant rate of change, which is going to be change in y over change in x. So 0 plus 1/2. Okay? And what is dx? So, again, we're modeling every point, right? Every one of these points. So for any arbitrary x here, the current value of x, what is my dx? What is dx? It's going to be x. It's going to be x. It's going to be how far we've gone into the current interval, in the first interval. It's going to be x. Or we could say x minus x initial. If we wanted and x initial is just 0, right? Change in x. Final value of x, which could be any x in the interval, minus starting value, and x is 0. So the equation for the first segment is 1/2 x. It has a rate of change of 1/2, and it's just going to, the area is just going to be always 1/2 of whatever x is. Okay, see if you can do the next two lines, all right? They're all going to have this. They're all going to have that form right there. You're going to have your initial value of y plus the change in y for however far you're going into that interval, right? M dx. See if you can write the next two lines. Back in your chair, looking at your smartphone are not options. What's looking at first? Just staring at the screen, nothing's going to come to you mentally. You have to write, think, and talk. What's the initial area in the second interval? Anybody get it? Yeah. Right, which is? All right, at least one person's got it. 0.25 is our initial area in the second interval, plus what's the constant rate of change in this interval? Change in y over change in x. It's going to be 1 minus, so 0.75 over point, is it 0.375? Change in y, 1 minus 0.25 is 0.75 divided by change in x of 1/2. Oh, so no, it's 1.5. So 1.5? 1.5. The constant rate of change in the second interval. You got to get the ordered pair at the end, the ordered pair at the beginning, take the change in y over the change in x. And then what's our dx then? For any x value, how far we're going dx into the second interval? Thank you. X minus 0.5. Third interval. We start at area of 1. What's the rate of change in the third interval? Anyone got it? What is it? 4.5. Change in y over the change in x for that third interval. And that's going to be x minus 1. Okay, so we've done this before. We've done this before, and it's all based on the principle that your new y in the given interval is going to be the initial y plus whatever change in y you have in that interval. It could be any change in y within that interval, and that's why we have x minus 0.5, x minus 1. Okay, I hope you wrote that down, and you can, if you didn't catch it now, you can study it later. We got to move on. So now what we want to do is we want to do this same thing with one expression. One expression for the rate, and one expression for the approximate accumulation. So I'm showing, so it looks like large intervals, but it's just arbitrary. So we don't know what delta x is. Delta x could be anything here, but I'm showing just a couple intervals so we can really see the difference between g and f. Okay, so what kind of function is displayed by f, the red graph? What kind of function is that? Exact accumulation. And then the blue graph g? Approximate accumulation. Okay, good. So what we want to do now is, so we're just going to look at we're thinking about any arbitrary interval. And we want to write what the function g is for any arbitrary interval. So here we are. I'm going to pick this interval here from whatever this x value is to that one up there. And so now this is the current value of x. It could be anywhere in this interval, and this could be any interval. So x could be anywhere in that interval, and that could represent any interval. So we're totally generalized here. So for every x value, we want the associated constant rate of the approximate accumulation. Constant rate is calculated as, how do we calculate the constant rate? Change in y over change in x. Change in y over change in x. So the question is, in any interval, at any value of x within that interval, how do we do this? We have the tools. We have everything we need. So this is going to be, in terms of our approximate rate function, this is going to be the general structure of it. It's going to be a change in y over change in x for the current interval. So here's how we can represent change in x, and then here's the change in y. Again, this is not necessarily the second interval. This can be any interval where the current value of x is. This could be any interval. This could be the third, the 10th, the 5th. It doesn't matter. This could be any interval. So if we want to get how are we going to get, in general, get the change in y and the change in x? We need those coordinates of those points. Okay, so it's your job to write the coordinates of those points. Again, this could be any interval where x is. So this could be the third interval, it could be the 8th, it could be the 12th, it could be the 100th interval. How can you write the coordinates of those points? Who has learned something so far this semester? Go, write the coordinates of those points. It can be any interval. Yeah, exact expressions that give those exactly. You're not counting tick marks on the graph. This could be any width of interval. This could be any interval. This could be any x value starting and ending. Start with this point. See if you can get the coordinates of this point right here. Tell me what you got. Good. Good. Got it? What's just get the x coordinate of the first point. X coordinate of the first point. We have that. Don't have G. You can't use G. You use that. That's that. X actually be in the middle. Either way, you need the X value where? Left side of the curve. The X value is the left side of the curve. Okay, so in the current interval, we need this x coordinate. What is it? Left of x. Left of x is the x coordinate at the left side of the current interval. And then the corresponding y coordinate is f of left of x. Keep going. So now what are the coordinates of that point? What are the coordinates of that point? Okay, don't use right x. We don't have right x. Okay? So, how do you get the x coordinate of this point? You should be able to do it. This is left of x. Then what's this x coordinate? It's delta x more, right? It's delta x more. So this x coordinate is left of x plus delta x. And what's the y coordinate? F of that. F of that. So then what's the rate of change? So now we can set up the rate of change. It's going to be change in y, or final y minus initial y, over change in x, which is just, we know what that is, delta x. So we get final y minus initial y over the change in x. That'll be our rate. Now that works in any interval because our left x function gives us the right x value for any interval. So that works in any interval. Okay, so then the last thing is we want to write the function g, the approximate accumulation function, by writing the definition of the linear segment in an arbitrary interval. Okay, so in this interval right here, how would you write the definition of that segment right there, just like we did earlier, but now using expressions for these coordinates? And because of left of x, that will be true for every interval. Okay, so can you do it? Last thing. What is g of x? What is g of x? Okay, I'm just putting the screen up so that I can write. It's not a cue for you to pack up, okay? I'm just putting the screen up so I can write. Goes back to this. Our g of x is defining every y coordinate. So it's going to be y initial plus the change in y. What's y initial? Not left x. What's y initial? F of left of x. That's y initial. Plus dy. What's dy? So it's m again, m dx. What's m? We just did it. There's m right there, the rate in the current interval. So we can just write that. We already did it. Times however far we've gone in that current interval, dx. How do we express it? Dx minus same dx that we had in the accumulation function. That's our dx, x minus left x. So this then defines the whole piecewise approximate accumulation function. Starting value of y plus m times dx. How far you've gone in that current interval. Okay, homework is posted. See you Friday.